Hello folks, how's everybody? Hope you're doing fine. Want to announce today first, again, that we have a conference coming up in Lusaka. That will be April the 4th. You can find more information there at that link there. Okay, so if you want to participate, well, better make plans starting today. Okay, and we usually have a lot of fun at those conferences. I want to get quickly into some of the comments. I'm not going to deal with too many comments today, but I do want to address a couple of them. And here's one of them. If I can get it up here. There it goes. And it says, do you believe that there are such things as spiritual beings, like man is a spiritual being with a body? But angels are pure spirit. Okay, I think it is okay for us to conceive of them as concepts because concepts exist, but not as physical. Okay, this is his notion, this gentleman. And what do we reply? Well, I'll put it next to his so we can see it side by side. You know, if an angel wants to exist, he's got to fulfill the definition of the word exist. We have to define the word exist. And as you can see, it's defined as physical presence. It requires an object. Only objects can be said to exist, and concepts cannot be said to exist, not in science. And as you can see by that definition, there is no provision for belief. Okay? Something does not exist because you believe that it exists. Okay? Now you might say it exists for me, you know, because you believe in it, right? So you have this notion that something exists, a cat exists, or a dog exists, or a table exists, because you believe that it exists. Okay, that's your opinion. Because the dog exists for you, it doesn't exist for this other person who says, no, that dog that you're talking about doesn't exist. And so we get into opinions and beliefs, and that's why it's not scientific. It's religion. In science, it's very simple. We define the word exist. If it meets a specification, it exists by definition. The definition is, one more time, put it up there just so everybody gets it, physical presence. It has to be an object, cannot be in a concept. If an angel wants to exist, the angel has to be an object to begin with. It's got to have shape like that one there. And then we can talk about whether it has location or not. Okay, but that's the first condition, is that it has to be an object. Okay, I hope that settles a lot of stuff. You don't have to believe in my theory. You don't have to accept my theory. You don't have to agree to the theory. Okay, to the definition. If you don't like the definition, you have a single recourse. That's to provide an alternative definition that we can use consistently, rationally, scientifically. Second comment, fellow says something. Ooh, I'm having trouble getting these things up there today. Second individual says, regarding the block universe, right? Determinism and seemingly probabilistic behavior are not mutually exclusive if you consider an external agent. And this individual goes through an explanation of how someone designed something out there and you don't know about it, etc., etc. You know, I'm not going to go through his entire argument. All I'm going to say, in fact, you can read it maybe in one of the comments there. What do we say to that? Well, we say that it doesn't matter whether you know or not, and it doesn't matter, the issue is not whether someone forced you to do something. Supreme being out there, the Klingons, the guys who created this hologram here, we don't care. We're not talking about you being forced to do something at gunpoint. We're saying that someone knows what you're going to do already without a shadow of a doubt, without an error. Okay? And that's different than knowing for sure. You know, some people say, well, you know, if I leave my cookies out there for my little girl, I know she's going to grab those cookies. That's not knowing. Because for all we know, you know, your girl trips, doesn't make it to the cookies, makes it to the hospital instead, and the cookies are still there. So you did not know. Okay? Again, people confuse intelligent guesses with knowing. Knowing means that you run an experiment and know without, and you can predict the results without a shadow of a doubt. And if there's an error, then you did not predict. You did not know. You just had an intelligent guess. People confuse those two things. Now, here, let me put it in two contexts. Here's the first context. And here we have Mr. Felix. And he's going to throw this horseshoe, and it's going to go right through the window. He's going to commit a crime. He's going to break a window in that market. Okay? Now, does Felix have a choice? Does he have free will? Or is he following the spec that I wrote for him? If I drew this, if I made this film, does Felix have any choice? Does he have free will? That's the first issue. The second issue is this one. Here we have God, and he's got a filing cabinet, okay, up there in heaven. And he's got your file. It doesn't mean that God forced you to do something. It means God knows exactly what you're going to do because it's already printed on his file cabinet. He knows what you're going to do exactly. He knows what you're thinking. He knows when you're sinning already before you sinned. And so if God is omniscient, there is no way you can avoid not having free will. And that's the issue that's been bugging theists for, 2,000 years now. They cannot reconcile God's omniscience with free will, and they've been debating this issue for that long, and it hasn't been settled. You can look it up. I mean, you'll find out that they're still debating the issue, and they'll invoke authority, and they'll say, look, this is what Augustine said, this is what Aquinas said, and so on. They'll go through the whole rigmarole. Why? Because they haven't settled it. It's just that simple. And you can't solve it because the issue is not that God's going to force you to do something. The issue is that God knows that you're going to do it no matter what. So in that sense, you are more or less like Felix there. Okay, that's it for comments. Let me get into the subject matter. And the subject matter today is Mr. St. Thomas Aquinas. And I'm saying that he invented quantum mechanics, title of this presentation. And you say, what does Aquinas have to do with quantum mechanics? Well, very simple. He introduced angels. And you say, well, what do angels have to do with quantum mechanics? Well, in order to explain certain magical features of angels, what Aquinas did was invoke points and lines of geometry. He went to the Greeks, he used those arguments to show that, you can prove, through argument, etc., that angels have all these magical properties. They can go through things, many of them can be at the same place at the same time. One angel can be at several places at the same time, etc., which sounds a lot like quantum mechanic particles. So it's up to the non-believer, the naysayer, or devil's advocate, to tell me in what way particles of quantum mechanics and angels of Mr. Aquinas 1,000 years ago, how they're any different. They had the same properties. And the issue is that he based it on what the Greeks had developed. Now, the guy who's known mostly for developing geometry from the Greeks is Euclid, okay? And he wrote a book, 3rd century BC, titled Elements, the Elements of Geometry. And, people give him a lot of credit. And I give Euclid very little credit because I think he was a guy who simply compiled it all, put it all together, what he learned in school in those days, the general knowledge that was around, and he just put it in a book. Now, whether he put any new material in there, something of his, it's hard to know, but for sure a lot of that stuff already was known by just about every Greek that dealt with philosophy, geometry, etc., and mathematics. So Euclid was not the first guy to come up with all this stuff by a long shot. And here I made a little chart that puts it in the right perspective, okay? Here you have the Greeks from different ages. You have from the 6th century all the way to Euclid, which is around the 3rd century. And you've heard of some of these names here and there. And you'll see that the Greeks already had quite a mastery of geometry by the time Euclid was born. And you have the Ionian school, the Pythagorean school, the Eleatic school, and you'll see the little colors there. It shows you more or less where these people set their schools, the center of their schools. Okay, and you know the Greeks traveled around the Mediterranean, so they knew they moved around. They were not a static society, especially the rich people. They moved around. And yeah, by the time we get to Euclid, you know, he just learned what all these people had already developed. In fact, I would not even give credit to these early Greeks because they probably inherited a lot of that stuff from the Egyptians and the Persians, who probably inherited some of that stuff or learned that stuff from the Indians or the East. You know, it's very hard to know. We lose track of who really developed what. The point is that by the time it gets to Euclid, he formalizes all this knowledge, and you know he's really not the first, but one of the books or one of the series of books or one of the schools he relies upon is Aristotle's. Aristotle, he founded what is known as the Lyceum in Athens. And it's a little quick story on that, just in case, so that we put it in the right perspective. Aristotle was the tutor of Alexander the Great when he was a kid. And Philip II, Aristotle's father, brought him over and says, you know, I want you to be my kid's teacher. And so, you know, Alexander learned a lot from Aristotle, and they became friends. So when Philip died, he was murdered, you know, coup d'etat, and Alexander took over. By that time, Athens and the Thebans, they rebelled. They rebelled against the Macedonians. You keep in mind that Aristotle was a Macedonian, okay? And what happened was that they rebelled against the Macedonians, tried to get them off their shoulder, you know. And at that moment in time, you know, Alexander was in charge of the troops. He went down there, he beat the hell out of the Thebans, and the Athenians, they kind of backed off and you know, continued paying tribute to Macedonia. And at that time, that's when Aristotle comes to Athens, around that time. And he comes to the Lyceum. Lyceum was a place where all the Greeks, all the Athenians would gather to discuss politics and do gymnastics and philosophize, you know, about these issues, physics and so on, geometry. And when Aristotle comes in there, he just turns it officially into a school, and he gave lectures there. Okay, some of the students took notes, and they wrote books. And so a lot of these books are what we have today. A lot of people think that Aristotle was this great genius, you know, that invented all this stuff. Personally, I don't think so. I think if you look up history, you'll find out that a lot of those books just come from the school known as the Lyceum, and there were lots of students, lots of brains in there. They developed things, and this whole body of knowledge is all attributed to Aristotle. In fact, about a little over 10 years after Aristotle came to Athens, he was kicked out. He had to run for his life because Alexander had been murdered in Persia, and Athenians rebelled against Macedonia, and Macedonia beat them, and that was the end of what we know today as the the classical Athens. Okay? This is when Athens finished its classical period with the death or the exile, voluntary exile of Aristotle. Anyways, the deal here is that, by the way, here's got a little picture here of what the Lyceum looks like today. Just the foundations are left, and this is what an artist thought, it looked like in those days. Lots of people gathering, and they would talk about physics and politics and religion, who knows what. Okay, so it was a gathering place, a marketplace, so to speak, and people just went there to philosophize. Anyways, what Aristotle did, he developed a language to try to figure out causes and mechanisms. And he wanted to know why things happen and what causes them to happen, which is the right notion for physics. The mathematicians today dismiss that as philosophy. And it's the other way around. What they do is philosophy. Mathematics, all that stuff, if anything, is part of a philosophy we call religion. It has nothing to do with science. Science is about explaining, and that's what Aristotle tried to do. In order to do so, he developed a certain, especially physics, right? What he tried to do was define some terms that he thought he would need in order to make his case. And he defined words that I personally don't have any use for, and physics in general I think has no use for any of these terms. These terms have to do with geometry, but not with physics. And geometry is not a branch of physics, okay? Geometry is a branch of mathematics, and it should stay there. And none of those two belong to science, let alone to physics. In science we explain. Physics we explain causes and mechanisms, which is what Aristotle tried to do. Mathematics and geometry only describe. It doesn't explain anything. Okay, so that's the problem with geometry and math, why they're not part of physics, why they're not the language of physics, why they're not even a part of science. Okay, I hope that's clear. And you don't have to agree, you just have to defend your point. Okay. Anyways, these are the words that Aristotle thought were important and the ones he defined, and you will see that they are related to the point and the line of geometry. So you can get a good guess that Euclid borrowed a lot of stuff, if not from Aristotle, at least from the entire Lyceum, the whole school that Aristotle created. And so he defines things like together, things in one place, apart, things in different places. Okay, very, very profound. Okay, contact, touch. Okay, extremities are together. Okay, very simple, straightforward. I think those are. I've summarized these because he writes a little more, right? Here we get two difficult ones, which I outlined in green there because they are a little tricky. And in the first one, you should really leave the red part out, the part that's underlined in red, because without that sentence, it's easier to read. Okay, so if you say that which a changing thing naturally reaches before it reaches that to which it changes last. Okay, it's easier to read that way. May not make any sense to you right now. Give me a second. I'll illustrate it for you. Second one, in succession, which is somewhat different than between, right? After the beginning, in position or in form, and there is nothing of the same kind as itself between it and that to which it is in succession. What does this all mean? I decided to illustrate it because these are somewhat, tongue twisters. See if I can get this thing here. So here's my illustration of this so that you can get it, so you don't have to break your brains trying to figure out what he's saying. You have the top one is in succession, the bottom one is in between. What Aristotle is saying is if something moves with, for example, uniform motion, okay, if they're stuck together, if they're touching, then you have succession. Not really touching, but if there's no space between them, then it's which is essentially the definition of touch, right? Then they're in succession. Otherwise, if one moves and the other one separates somehow within a body, then we have what he calls between. Okay, and you have to keep in mind that Aristotle did not believe in empty space. He believed that as soon as something moves, something occupies its space, that's its place, right? So it's just that the in-between is the object that occupied the space. That's what he's saying. And now if it's the same object, if both objects are moving simultaneously, then there is no in-between. In-between happens only when there's a space that something else fills in. That's the notion he wants to give to you, okay? And again, I don't know how important those are, but they were important for his definition. Here it is again. And what else does he say? Well, he says contiguous and continuous. Contiguous, thing that is in succession and touches. If he's going to talk about touch, he's no longer talking about concepts. See, in the case of between and in succession, he's emphasizing the first one, the word change. In the second one, he's emphasizing, what was the word? The position. Okay, he's talking about position. Okay, so it's a little different than the first three, where he talks about a thing being in a certain place or contact, two things touching each other. Contiguous is the same notion here. He's using things, okay, not concepts. He's not saying that love is touching intelligence. He's saying that a thing touches another thing, a rock touches a tree. Okay, that's what he's talking about. And he's obviously going to talk about points and lines. That's where he's headed with all this. Geometry, again, okay? And the important word is continuous. Why? Because he's gonna make several arguments. One argument is the argument of infinity. That's what he's going towards. He's trying to head towards this word infinity. And that's a big problem, because infinity has to do, as he's going to be using it, with a number line. It's got to do with time. It's got to do with motion. Okay? Incessant motion, which he calls infinite motion or infinity. And that's where we get the words confused. And that's where he gets away from geometry, because what does all that have to do with geometry? Okay? He's going to talk about location instead of talking about point, the dot. Okay? So when he needs to talk about touch, he uses the dot. And when he needs to talk about infinity, etc., well, he can't use the dot unless you're talking about counting dots, in which he's talking about numbers, which has nothing really to do with geometry proper, because geometry above all needs a shape. It's the study of shapes and sizes. Okay. Anyways, the word continuous. Things are called continuous when the touching limits of each become one and the same. He's talking about an object that is made of a single piece, as I like to put it, in physical terms. Continuity is impossible if these extremities are two. Okay? So essentially he's saying, talking about objects, and he's saying it's got to be made of a single piece in order for it to meet the definition, his definition of continuity, okay? Of continuous. Okay, let's move on here. Let's see if I can get this other one here. And what is he referring to? He's referring to the line. He's saying the line is made of a single piece. And it's interesting how he puts that in this following context. Listen to this one. This is important, because suddenly he pulls a rabbit out of the hat without you knowing. He says, if, as some say, point and unit have an independent existence of their own, it is impossible for the two to be identical. For points can touch, while units can only be in succession. Okay? So in the case of units, he's saying one's right after another. He's talking about numbers. In the case of points, dots, right? He said they can touch, because what? We're talking about physical objects. We're not talking about locations touching each other. We're talking about dots touching each other. Let's keep that in mind. Moreover, there can always be something between points. Oh, what can be between 2 points? For all lines are intermediate between points. What separates 2 points? A line. What is a line? Distance. He's talking about distance. He calls it a line. He's using geometric objects such as line to separate 2 points. Okay? What's he talking about? He's talking about distance, but he uses the line as a pictorial representation of that distance. Suddenly he introduces geometry, shapes, where it has no requirement. There's no necessity to introduce a line in this context. Okay? And whereas that is not necessary that there should possibly be anything between units. What is he talking about? Numbers. For there can be nothing between the numbers 1 and 2. So the numbers 1 and 2 are not separated by distance or lines because one comes right after another. Okay? Whereas between two dots, right? What do you call them? Points? Between two dots, if there is a distance, well, that distance is a line. So you figure it out. What does the line mean in that concept if not distance? He is talking about distance. Anyways, this is the starting point, okay? And from here, here, this is where it leads. I just want to summarize this, okay? This is what Aristotle is referring to. He's using point and line to talk about not geometry. He's talking about location, distance, motion, time, numbers. The number line. That's the context of where all this is headed to. And he's going to be using that in the next couple books that he writes. He wrote this book, Physics, composed of 8 books. And this is in book 5. By the time he gets to book 8, well, he's developed this in a geometric sense, or he uses geometric arguments, so point and line in lieu to pictorially represent location, distance, motion, and time, and number. Really the number line. That's what he's talking about, because he's going to talk about infinity, okay? Okay, so that's the starting point, and it's the starting point for Mr. Aquinas. And the other day I talked about, what Aquinas was doing here, right? He was talking about angels, and these are some of the properties he assigns to angels. They're all together. Whether he asks these questions, he tries to answer these questions, whether the angels are incorporeal, whether they're composed of matter and form, whether they're infinite numbers of them or great numbers of them. They differ in types, right? Species, whether an angel has a location where it's in a place, or whether an angel can be at several places at once, or whether many angels can be at one place, and whether it passes through an intermediate space. Does an angel go from A to C and passes through B, or does it go directly to C? And whether the movement of an angel is instantaneous. And for some strange reason, these are the same questions that we have the followers of Mr. Bohr. Right? He's one of the key founders of quantum mechanics, and all those questions apply to particles as well. And you probably heard a lot of those notions, those questions as applied to quantum mechanics, or being addressed today by quantum mechanics. Okay, so this is again the starting point, and here we have Mr. Tom again. And he goes with that first question, whether an angel is altogether incorporeal. Is an angel made of substance? Is it made of something, whatever, or is he? I hate to say it because I don't want to put words in his mouth, but what he's saying is, is an angel a concept or is it an object? Object, that which has shape, and a concept is that which doesn't. And so if it's corporeal, then it's an object. Very simple. And it's a black or white. And the question is there anything in between? Okay, and so he says every body is limited to here and now. Okay, so you have a temporal and a physical location. Okay, that's for a body. Okay, the perfection of the universe requires the existence of an incorporeal creature. It requires it. It sounds a lot like quantum mechanics so far. It requires incorporeal creatures, particles, right? Incorporeal substances rank between God and corporeal creatures. Between us and God, there's all these intermediate grays, okay, these maybes, okay? The angels compared to God are material and corporeal. Not, however, as if anything corporeal existed in them. An angel is called an ever-mobile substance, and not as if he were sometimes actually and sometimes potentially as we are. Okay? So he's saying the angel is somewhere in between God and us. For us, he is spiritual. He is insubstantial, incorporeal. For God, he is corporeal. He is substantial. He is made out of something or matter. God can see him or sees his body or whatever. So for God, he's material, but for us, he is spiritual. You figure it out. It's like covering all the bases, trying to get the best of both worlds. To be circumscribed by local limits belongs to bodies only. Okay, so you can't be circumscribed by limits, because then you become, I guess, human. You become a real material thing. And you don't want to really hold the angel to that. And angel's above that, because he's not God, but he's between God and humans, right? Okay, so what does quantum mechanics say to all this? Does it have a parallel? And I think it does. And here you see some. Here's the people, the disciples of Mr. Bohr, and they have invented what is known as the virtual particle. What is a virtual particle? A transient quantum fluctuation that exhibits some of the characteristics of an ordinary particle while having its existence limited by the uncertainty principle, which is down there below. The term is somewhat loose and vaguely defined. No kidding. Maybe self-servingly. Real particles are better understood to be excitations of the underlying quantum fields. Virtual particles are also excitations of the underlying fields, but are temporary. They last only for a fleeting second, okay, or microsecond. The uncertainty principle says that we cannot measure the position and momentum of a particle with absolute precision simultaneously. The more accurately we know one of these values, the less accurately we know the other. That's essentially the notion that they have of the uncertainty principle. And because of this rock solid principle, we invented virtual particles. We allow them to exist for whatever time they want, because uncertainty principle allows for it. And we haven't stopped at the virtual particle. We have also invented the quasi or quasi particle. Okay. And a quasi-particle, collective excitations, emergent phenomena that occur when a microscopically complicated system, such as a solid, behaves as if it contained different weakly interacting particles in free space. Okay, so again, all these ghosts and goblins that quantum mechanics has resemble quite a bit the angels that Mr. Aquinas invented. And so the question is, what is a quasi-particle? Is it an angel, just like Aquinas said, or is it a field that's vibrating? Is it a bunch of numbers that are vibrating? Is it a particle, like that red dot in the center, or is it a leprechaun? I mean, what is a quasi-particle? What are we talking about? It's like these people have invented all these notions just to get around the explanations. We cannot understand with these notions that these people developed. We cannot understand their explanation. We cannot figure what their physical interpretation is if they're going to use quasi-particles and if they're going to use virtual particles. Because what are they saying? They're saying, well, the particle just pops in from the void whenever it wants to. Whenever we're trying to do something, suddenly another particle pops in. We don't see it. We can't measure it. We infer that it's there because something happened, so the particle came in and then went back out. Sounds a lot like an angel. I mean, the angel moved my curtain. I'm sure of that, okay? I'm sure that the angel moved my curtain. Did you take a picture of him? Did you grab him? Did you talk to him? No, he went back and turned into space again. So he came, he moved the curtain and just went out. And so I have to say, well, that was done by, well, if it wasn't done by a virtual particle, it had to be done by an angel, right? Or maybe I should just shut the window. Anyways, quantum mechanics. This is what they have in mind. The mechanics, they say, look, we have this, sheet, the space-time sheet, and it's vibrating. It's all this vibration that forms the background, the vacuum, that's in the background. Okay, this is the vacuum energy. And from this vacuum energy, what we have is suddenly, a virtual particle pops out of there. And it goes something like this, see? You have the vibration of the waves, and suddenly two particles appear. Particle and antiparticle, of course, right? And they have opposite polarities, and so they come together and they collapse into nothing. They go back to being a wave or part of that vibration in the background. And from that same vibration comes a pair of particles that turn into real particles that do something in the real world for a fleeting second and then go back to becoming part of space or vacuum or whatever they call it. And here's another vision of that. You have a little wave, turns into a particle and back to a wave and back and forth. And these things pop in from the void. And that's why these people cannot give you a classical or rational, as I call it, a rational answer to any physical interpretation. What they say is, look, particles appear from the void, and it's all that fluctuation that's going on in the vacuum that's happening. Okay, and that's the reason that we cannot explain it in rational terms, in terms that you would understand. The math doesn't lie, it's there, and the experiments prove it. But we cannot explain it to you except with these virtual particles that somehow, pop in and go out, and, it's all these waves that turn into particle momentarily and then go back to being waves or field or energy or whatever nonsense word that has been invented. I think the best word is angel. I think, I think they're just trying to steal the Nobel Prize away from Mr. Aquinas. I mean, he deserves a Nobel Prize because he said it first and he said it with angels. These people say, well, what are we going to do now? Well, let's call it particle and we get rid of Aquinas completely. He doesn't, get his Nobel. We do it. All we did is just, give it new names? Is that it? Because it's still an angel. It's got the same powers and magical properties attributes, that the angels had. Anyways, so what is this vacuum? You wonder because you're saying, hold it, the vacuum is vibrating? I thought the vacuum was nothing. What is vacuum? And so you go up there and you look it up, and this is what Mr. Bohr and his disciples, let me get it right there, believe the vacuum is. This is the definition you get today. This is out of Wikipedia, but I guess it's the same everywhere. It doesn't matter. Vacuum is space. Okay, keep that word in mind, space. Vacuum is space devoid of matter. Oh, okay, so we have space that has matter. If we take all the matter out, we get what is called vacuum. Okay, got it. I think I got it. Okay, an approximation to such a vacuum is a region with a gaseous pressure much less than atmospheric pressure. Ooh, that's an approximation to vacuum, saying that one that has very little matter. Well, that's a wrong definition. That's just an approximation. The real definition is that first one. It's devoid of matter. That's vacuum. Okay, let's keep that in mind. Physicists often discuss ideal test results that would occur in a perfect vacuum, which they sometimes simply call vacuum or free space. Okay, keep those terms in mind if you can. Vacuum, free space, that's the same thing as perfect vacuum, no matter whatsoever. And use the term partial vacuum to refer to an actual imperfect vacuum as one might have in a laboratory or in space. Okay, yeah, I work with those. So you pump out lots of matter and you don't have a perfect vacuum, and they call that an imperfect vacuum or space. Because what is space? Space is that which still has matter. Vacuum is total absence of matter. Okay? In engineering and applied physics, on the other hand, vacuum refers to any space in which the pressure is considerably lower than atmospheric pressure. In other words, we have a little confusion because according to this, engineers and applied physicists, they say there's no such thing as a vacuum. We need something a little more practical, more pragmatic. And so our so-called vacuum is really not total vacuum. That vacuum is really full of particles, which means that vacuum is the same thing as that space there. Means that space has particles in it. Okay, that's what space is according to these definitions. Space, some particles, at least. Vacuum, total absence of particles. Why don't they just call it space? No, they call it vacuum and confuse you completely because they say, well, our vacuum is different than their vacuum. Their vacuum is a free vacuum, a total vacuum, a perfect vacuum, and our vacuum has some particles in it because we cannot achieve total vacuum, so we call it a vacuum. To confuse everybody. Okay, so we have a vacuum that is not a vacuum. We have a vacuum that is space. Space has particles. Vacuum doesn't, but their vacuum has particles in it. It just has less particles than atmospheric pressure. That's the notion. Okay, so what is a space thing? I mean, I want to know what space is now because that's the key word they use in this definition. So here we have the word space. Space is the boundless three-dimensional extent. What's an extent? Extent of what? And what do you mean space is three-dimensional? Are you saying it's like a cube? It's like a ball? It's like a pyramid? I mean, what do you mean three-dimensional? Space, I thought, was nothing, which is what the first definition says. Space, devoid of matter, it gives you a vacuum. So vacuum plus matter equals space. And now suddenly this space turns into a physical container of sorts. It's three-dimensional, okay, in which objects and events have relative position and direction. I don't know how an object can have, if space is an object itself, how can you say that objects occupy space if space is an object? Again, are we talking about a container? Is that what space is? And so he continues, or the definition continues, physical space is physical space. I mean, space made out of something physical is often conceived in three linear dimensions, although modern physicists usually consider it with time to be part of a boundless four-dimensional continuum known as space-time. Note the words they use, extent, continuum. I don't know what an extent is. I never was able to draw one, or I've never seen an illustration of a continuum. Okay, what are these words? They use these fancy words and we don't know what they're talking about. Space is an extent, space is a continuum. Then it says the concept of space. So I thought it was an object, but now it turns out that space is a concept. Is considered to be of fundamental importance to an understanding of the physical universe. Thank God. I'm glad that it's part of the foundations of physics, right? However, disagreement continues between philosophers over whether it is itself an entity, a relationship between entities, or part of a conceptual network. Okay, now how's that for a perfect definition, a unambiguous definition? Okay, I guess you can take that to the bank, right? Okay, but we continue. It turns out there's another, like a little corollary to it, and here we continue with that definition. And so what are they saying? They're saying that space is one of the few fundamental quantities in physics, meaning that it cannot be defined via other quantities because nothing more fundamental is known at the present. Okay, what they're saying is they don't know what space is made out of. Okay, on the other hand, it can be related to other fundamental quantities. Quantities? What are they saying, that space is a quantity? What are we talking about? It's an extent. It's a manifold or whatever they said, continuum, and a quantities. It's a quantity. So now I have no idea what a space is. Well, what do they mean by space? Thus, similar to other fundamental quantities, okay, like time and mass, space can be explored via measurement and experiment. So you need to measure something to figure out what space is? I thought you just need a good definition to know what space is. And how are you going to prove the existence of space through an experiment? What experiment are you going to run with space? What are you going to do? Take it to the lab and do, I don't know, juggle it? Juggle the particles of space? I don't know what experiment can you do with space? I don't know what you can do. Okay, today our three-dimensional space, big object, I hope you see it someday. It's a three-dimensional something out there called space, okay? Is viewed as embedded in a four-dimensional space-time. They put it outside your reach. The idea behind space-time is that time is hyperbolic orthogonal to each of the three spatial dimensions. My God. So we have this space-time that includes space, which is three-dimensional with some kind of container. They can't draw it, but they say it contains everything. You figure it out. Okay, so that's the story so far. Let's move on here. Good old Tom goes to the second question, second issue. I can get it up here. Okay, and it's whether an angel is composed of matter and form. What is an angel made out of? What is a particle made out of? Okay, I mean, so far the particle seems quite weird because it comes out of space whenever it wants to, goes back into space. We don't know what space is. They call it vacuums. Vacuum has different definitions. And they never define the vacuum. They just say it's space without particles. That's what vacuum is, whatever that is. You know, it says matter is not divisible into parts, except as regarded under quantity. Again, quantity. And without quantity, substance is indivisible. Okay? So essentially they're saying you can divide objects. Therefore, it would follow that the matter of spiritual things, who's talking about angels, right, is subject to quantity, which cannot be. Okay, so saying that, you know, in an angel, you cannot subdivide, you cannot cut in half. Because what? Because you may be cutting a concept. You know, can you chop love in half? That's more or less the notion that he's putting out here. Therefore, it is impossible that corporeal and spiritual things should have the same matter. So we're not made as the same matter as angels, okay? And I guess we're not made in the same matter as quantum particles, because, you know, we seem to have different properties than the quantum particles. Particles can be at two places at once. The particles that comprise me, you know, they can be at two places at once, but I can't be at two places at once. And that's kind of weird because these particles can and I can't. And they make me, I'm made of them. Okay? Okay, so he's essentially what I say, objects you can divide, concepts you can't. That's essentially what Aquinas is saying. So here we have an angel, okay? And the question is whether you can divide that angel, okay? And let's see if we can do that, because, see, you have a shape on the, there. You can see something there. There's a contrast. The angel's the white stuff in the center over there, okay? And what happens if we try to cut that in half? Here it is. Well, I cut it in half. I guess I was able to cut the angel in half. I mean, give me any object, I should be able to mentally cut it in half, slice it down to the middle, okay? I think I can do that with any object in the universe, even with a picture of an object, right? And of course, if the angel is representative of good, something that's nice, you know, you can't chop good in half. Okay, what are you chopping? Because good is a concept. I mean, can you chop love in half? Can you chop intelligence in half? You know, it doesn't make no sense. And this goes back to Aristotle, who said, you know, the definitions of continuous versus the definition of contiguous. And, you know, they apply to objects. You can't apply, see, if they have to touch, you can't extrapolate that property to concepts. You can't say love touched intelligence. You can't say that other than poetically. But you can't say that in physics, in science. And so, you know, again, you have to decide whether the angel is that little flapping thing that's got wings, you know, flying out here. I can see that thing, it's got shape. I can mentally cut it in half. But if the angel is just a pictorial representation of good, well, I can't chop good in half. And that's more or less what the problem Bohr has. You know, here we have, here's the field. So we're going to chop it in half. How's that? Okay, we chop the field in half. Does that make sense? Can you chop a concept such as a field? What is a field? Well, they say that a point or a particle is a vibrating field. It's an excited field. That's what that's what a particle is. And so why shouldn't I be able to chop it in half if it's just a particle? Of course, if it's a concept that is vibrating out there, for example here, let's see if I can put this up here. Here's the half a field of vibrating numbers. You have a field and a half a field. How's that? I mean, if a field is just a bunch of vibrating numbers, which is how it's defined, just a bunch of numbers coming out of and becoming weaker, farther and farther away from an object, then yes, you can't chop that in half. You can't chop values in half physically. You can chop them mathematically, but not physically. That's the point. Okay. So we've got a problem with these notions of going back and forth between objects and concepts, and that's essentially the problem that we have with quantum mechanics. And the guy who came up with all that stuff is obviously Mr. Aquinas. Already he had developed those notions almost 1,000 years ago. Anyways, here we have the math point. Getting back to geometry, we have the dot. And yeah, I can cut the dot in half. I'll have half a dot. But if the dot represents location, if that's just a pictorial representation of location, I don't think I can chop location in half. I mean, what meaning does that have? I mean, a dot I can chop, two-dimensional. And so it's now two-dimensional divided by 2. Can I chop an ordered pair? You know, have an X and Y, does it make sense to say, well, I'm going to chop it in half? You know, how many steps to the treasure chest? Well, it's 10 on the X-axis, 20 on the Y-axis, so I chop it in half. I leave 10 over here and then 20 over there. Does that make any sense? Chopping a concept such as an ordered pair, which represents, or which the dot represents. Does that make sense to chop it in half? And this is what these people are doing, essentially. I mean, when they go back and forth between math and physics, between geometry and physics, they bring in the dot when they need to explain something pictorially for you to see with your own eyes. And then they go back to the concept. And they jump back and forth, and people don't realize that that's what's happening, and that's why a lot of people don't understand a lot of this stuff, because they say, yeah, I didn't understand squat. Yeah, I sympathize with you, okay? Okay, where do we stop? Well, we don't stop. We have here Mr. Aquinas. He goes a step further, and he says, again in that saying, whether an angel is composed of matter and form, he says, it is further impossible for an intellectual substance to have any kind of matter. Angelic substances are above our intellect. And hence, our intellect cannot attain to comprehend them. You cannot understand this. What they're doing is, or what he's doing is placing God beyond your reach, or angels in this case, right? He's putting them beyond your reach. He's saying that you cannot even imagine this thing, so don't even try. Other people say, you know, one of the answers I got once is that if I could tell you what God is, then God wouldn't be so great. That's a good answer. That's the type of answer you'll get. You'll never know what God is. You won't know what an angel is because, you know, he doesn't put his finger on it. He just says, look, it's beyond your reach. You won't understand it, so don't even try. Okay, so, you know, a lot of atheists say, well, prove their existence then if you can't even make sense of what you're saying, okay? If you don't know what you're talking about. But see, it doesn't get relegated to religion only. Here we have Mr. Leonard Susskind. He's a Stanford professor of mathematical physics, which we know as mathemagics. And this is what he says as well. I mean, what did good old Mr. Aquinas say just now? He says, you know, I'm going to put that beyond your reach so you can't even question it. You cannot put me against the ropes and pummel me because I'm just going to put it beyond your mind's reach. So what do the quantum mechanics do? How do they explain stuff? Well, here you have it. He says more or less the same thing. He says, you and I evolved in a world of 3 dimensions. We can't visualize more dimensions. I can visualize 3 dimensions in my head, but I use X, Y, and Z to describe them mathematically. Note that he uses the word describe. Now I go to 4 dimensions or 5 dimensions. I can't visualize them anymore. I can't say, now close your eyes and view in your head 5 dimensions, because I can't do it either. So we're stuck needing mathematics because evolution didn't equip us to be able to visualize quantum mechanics. It didn't equip us to visualize 11-dimensional spacetimes. Evolution did this to us. Okay? Any difference between Mr. Aquinas and what we find in quantum mechanics? I don't think so. I think they're pretty much the same. I don't think the mathematicians of the Roaring Twenties who developed quantum mechanics, invented anything new. All these notions existed, 900 years ago, 800 years ago? They've been around for quite a while, and Aquinas wasn't the first one. There were other, like Boethius, I talked about the other day, that already had come up with a lot of these notions. They try to make sense of the invisible world around them. And they introduced angels. They had no other way of relating to some of the miracles that they saw happening around them. They said, what is light? What is fire? What is air? They can see all this stuff, and they said, oh, in many cases, not always, but they said angel. And then they had to say, well, how does the wind go from here to there? Does it go through an intermediate space? Well, it's the angel, goes through from here to there. They would explain it in terms of angel spirits, magical stuff from heaven, etc. What is different from quantum mechanics today? I mean, they're doing the same thing. They're saying, oh, virtual particle. Oh, that's a quasi-particle. Oh, that's a tachyon. It comes from the future. What is this? Is this science? Is this physics? Or is this more angelic stuff? And that's for you to decide. Anyways, I'm going to continue with some of the questions that Mr. Aquinas addressed. Okay? And I just want you to know that tomorrow I'm going under the knife. Okay, I'm going to have an operation. Some of you are aware, September, October, I was in the hospital for 3 weeks. I had a bacterial infection in my left leg, and during the course of that convalescence, the doctors discovered that I've got a bad vein. So they're going to operate my vein, they're going to take it out, or they're going to kill it inside the leg. And it's not a delicate operation like brain surgery or heart surgery, but whenever you're knocked out, you may not come back. So it's always, there is some risk, some danger always when you're totally anesthetized, okay? And so I'm going to be in there tomorrow, and we'll see if I come out of it. Hopefully I do, and I'll be back here on Sunday. So if you don't see me on Sunday, you know what happened. I never made it. Hopefully I do, and I'll see you on Sunday. We'll see you then. Bye-bye.